This is Dr. J. Mohan. I am from EC Department of Institute of Aeronautical Engineering. Today, going to discuss about the Laplace transform, 5th section. This under the topic of signals and stochastic process subject. Already we discussed about the property of Laplace transform. We should continue for the remaining property. Next property is represents a convolution in S domain of Laplace transform. Next property is time convolution and the multiplication property of Laplace transform. Partial theorem of Laplace transform. Solution of differential equation using Laplace transform. Up to this much, the Laplace transform property is getting to complete. This topic I referred from Signal, System and Communication, B. Lathi, and A.B. Openham, Signals and System. First case, that's a first property, convolution in S domain, property of Laplace transform. The convolution statement of Laplace transform in S domain is represented as multiplication property or modulation property of Laplace transform. This means the frequency convolution property of Laplace transform, it states that Laplace transform of product of two time domain signal is equal to the convolution of the respective Laplace transforms. Here I take for the two different signal. One is represented as x1 of t, another one is represented as x2 of t. Both the signal is represented as a continuous time signal. Then if we take for the both the signal in Laplace transform, it's produced x1 of s and x2 of s. Then these two signal, as per the statement, I should multiply for x1 of t and x2 of t. After that, I take to do for the Laplace transform. It's produced, the output is represented as 1 by 2 pi j x1 of s convolution of x2 of s. That means the input side of Laplace transform, if we are going to multiply with the two signal in the time domain, okay, this is Laplace transform system I represent for the h of s. The input side I make to multiply it with x1 of t in the time domain and x2 of t. Both it will be multiplied. We pass for the system in the Laplace transform. It's produced, the output is represented as a convolution of Laplace transform cases in S domain. So that is also is represented as a 2 pi j x1 of s convolution of x2 of s. Okay, so this is a statement of convolution property of S domain in Laplace transform. So this statement we need to prove. In this case, I should take for the inverse Laplace transform. The inverse Laplace transform of x1 of s. See, I take for the capital letter x1 of s. We do for the inverse Laplace transform. It's equal to x1 of t. So this x1 of t is equal to 1 by 2 pi j integration of limit sigma minus j infinitive to sigma plus j infinitive x1 of e power pt dp. So we should take for the two different signal. That's why the first signal I should take for the p terms. So this is similar only for x of s in terms of inverse case. Next, from the definition of Laplace transform, the Laplace transform of two signal multiplication is equal to, for as per the definition of Laplace transform, I should write x of s. So this is equal to Laplace transform of x of t equal to integration of minus infinity to plus infinity x of t e power minus st dt we wrote. So this instead of x of t, I take for the x1 of t into x2 of t. Okay. So as per the statement of convolution cases, two signal in the time domain, if we multiply it, that case I make to give us a x1 of x of t. So here I substitute for insist of x of t, x1 of t into x2 of t is equal to integration of minus into plus into instead of x of t, I should substitute x1 of t, x2 of t e power minus st dt. We know the x1 of t, the formula of x1 of t in the inverse Laplace transform, here we wrote. So these terms we should substitute for this equation. So what I am doing? So x1 of t, instead of x1 of t, I should substitute 1 by 2 pi j integration of sigma minus j infinity to sigma plus j infinity x1 of t e power pt dp. So here I use for the x1 because of this is x1. Okay. So then remaining terms I should write same like that one. That is x2 of t e power minus st dt. This integration also I write for the integration of minus into plus into. Then rearrange the order of integration. This integration I put for the inside and this integration I take for the outside. For this integration came for here. This will be go for inside. At the same time, this is x1 of t. There is no action here. I take it out for the x1 of p also and outside. So now I write for the rearrange the equation 1 by 2 pi j. I take it out integration of sigma minus j infinity to sigma plus j into x1 of p. Then integration of minus into plus into x2 of t e power minus s minus of p t dt and dp I wrote. Okay. Now you can see this term. What we are going to write, if you have the s term, then we write for the s in the Laplace transform. See, the x of s equal to integration of minus into plus into x of t e power minus st dt, right? Here I have the s, that's why I write for the x of capital letter x of s. So in this term, what is there? S minus of p is there. So that's why I write for the x2 of s minus of p. Okay. So this term I make to write for the x2 of s minus of p. So this is equal to, that means Laplace transform of x1 of t and x2 of t is equal to 1 by 2 pi j integration of sigma minus j infinity to sigma plus j into x1 of p, x2 of s minus of p dp I make to write. Now you can see this term what will be happen. So this entire term what will be going to represent. This is in the case of time convolution. We know that time convolution, what the formula is represent. The time convolution is equal to the time convolution of the signal. For we take for the signal, that is a system, we pass for the x of t. The system response is represents h of t. This is equal to y of t. The y of t is equal to x of t in convolution of h of t. We wrote as a system case of LTI. So in this same case, I make to write as y of t is equal to x of t convolution of h of t. This value is equal to integration of minus into plus into x of tau h of t minus of tau d tau we write. So this equation is represented as a x of t convolution of h of t we wrote. So same like that one we got for the values, that is integration of minus into plus into that is sigma minus j infinity to sigma plus j infinity x1 of p, x2 of s minus of p dp is there. So that's why I should write this term as x1 of s convolution of x2 of s as per the statement as linear convolution in the LTI system. So now I should put here for Laplace transform of x1 of t into x2 of t is equal to 1 by 2 pi j, that will be not getting to change, x1 of s convolution of x2 of s. Now we should prove the time convolution in terms of input side. If we are going to multiply with two signal in the Laplace domain, the output side it is going to have for the convolution in s domain of both the signal. So into 1 by 2 pi j. Then this is the way we prove for the Laplace transform of convolution state. We take for the some example. Okay, using convolution in S domain property of Laplace transform, find the Laplace transform of function x of t is equal to del of t into sine omega t. So two signal we are using, del of t as well as of sine omega t. So del of t of Laplace transform we know 1. How is represent? That is Laplace transform of x of t is equal to x of s. This formula we know well, that is minus into plus due x of t e power minus st dt we wrote. So now x of t is equal to del of t, right? That del of t we know, that is del of t is equal to 1 when t equal to 0, 0 otherwise. Only t equal to 0 position only the signal is present. So now x of t we should substitute for the del of t. Now this case I should write integration of t equal to 0 del of t e power minus st dt. Now the terms t equal to 0, the del value is equal to 1. Okay, t equal to 0, del of t is equal to 1, e power s t dt, but t tends to 0. Now if we substitute t tends to 0 to here, what you are getting, then integration is represented as a t equal to 1. So that's why we got for the only one value. So now Laplace transform of del of t is equal to 1. I should write here Laplace transform of del of t is equal to 1. And at the same time, to take for the Laplace transform of sine omega t, same like that one we write. Sine omega t is represented as a e power j omega minus e power minus j omega divided by 2j. That is sine of omega t. I wrote like that one. This value we should substitute for the Laplace transform condition. For x of t, here I take for the sine omega t. Sine omega t. This sine omega t should apply for here. Here is sine omega t. Then here is represented as a, that is insist of 1. This is we represent for the minus into 2 plus into 2. Sine omega t is represented as a e power j omega t minus of e power minus j omega t divided by 2j. Then after doing for the integration, substituting for the limit, then finally we got for the Laplace transform of sine omega t equal to omega divided by s square plus omega square. Now we got for the two signal. So both the signal it will be multiplied. Now I should write as a Laplace transform of multiplication of two times signal. It's is represented as Laplace transform of del of t into sine omega t. Okay, so this is equal to that we know the formula in the case of convolution cases. So this is represented as x1 of s. This is convolution of x2 of s. If you take Laplace transform, multiply with 1 by 2 pi j. Okay, so then we know this del of t is equal to 1. Sine omega t is equal to omega divided by s square plus omega square. Just you can substitute. Then we got for the convolution 1 into this is this case 1 by 2 pi j. 1 into the convolution of our Laplace transform of sine omega t is represented as a 1 convolution of omega divided by s square plus omega square. The 1 into convolution is represented as the same like that one. So finally I write 2 pi j multiplication of omega divided by s square plus omega square. That's it. So this is Laplace transform of del of t into sine omega t. Okay. So this value it is represented as a convolution case of Laplace transform. Finally I wrote the Laplace transform of del of t sine omega t equal to 1 by 2 pi j omega divided by s square plus omega square. Okay. Then you take for the another property. Here I taking for the another product with using the differentiation in time domain property of Laplace transform. Find the Laplace transform. X of t I take for the del of t, then x of t d by dt of del of t I take two signal. X of t del of t, then del of t is equal to d by dt u of t I make to write. Okay. If the relation between the u of t and del of t is equal to differentiation with d by dt of u of t we got for the del of t. This is the relation between the unit step signal and unit impulse signal. I like that one. I make to take here. The Laplace transform of u of t is equal to 1 by s. This is we studied for the last session. By using this time derivative property of Laplace transform, d by x of t Laplace transform of s x of s is equal to, that is derivative of x of t in the time domain in the Laplace transform is equal to s into x of s minus x of 0 minus. So we should substitute that cases. Then after we represent for the Laplace transform for the both the side of the relation between the u of t as well as of del of t. So Laplace transform of del of t is equal to Laplace transform of d by dt of u of t. So s L u of s minus 0 is equal to u of s, we know Laplace transform of u of t is equal to u of s, that value equal to 1 by s. So the already is s is that these two s's are getting to cancel. Finally we have for the 1. So if we do for the differentiation in time domain of Laplace transform in the case of u of t, finally you got for the 1 value. Okay. So next case, time convolution and multiplication property of Laplace transform. Previously we done for the time multiplication. Now we done for the time convolution in the input side. That means the Laplace transform. Okay, Laplace transform, that is x, that is h of s, around h of s we given for the input x of t. It's produced for the capital letter y of s. That y of s is equal to x of s convolution of h of s. This is we studied for the last property. Now this property in the input side I make to do for the convolution, that is h2, that is x2 t convolution of x1 of t. The output side, what will be going to getting for the output side? The output side is represented as a multiplication of what you are going to given for the two signal in the s domain, x1 of s into x2 of s. That is called for the time convolution and multiplication property of Laplace transform. First, we go for the statement. The time convolution property of Laplace transform state that the Laplace transform of convolution of two signal in a time domain is equal to the product of their respective Laplace transform. That means the input side, if you give for the convolution input of two cases, x1 of t and convolution of x2 of t, its produce the output is product of their respective Laplace transform. This is x1 of t Laplace transform is x1 of s, x2 of t Laplace transform is x2 of s. So this product, that is a x1 of t into x2 of t, that is called for the product of the respective Laplace transform. In this case also I am going to take for the two signal, one is x1 of t and x2 of t in the time domain of continuous time cases. If we take for the Laplace transform of x1 of t is represented as x1 of s, x2 of t Laplace transform is represented as x2 of s. Now as per the statement of time convolution and multiplication property of Laplace transform, x1 of t convolution of x2 of t is equal to product of x1 of s and x2 of s of Laplace transform. We need to prove for this statement. Now I take for the two signal x1 of t and x2 of t of time based signal. The two signal I represent as a two time domain causal signals. Then their convolution is defined as x1 of t convolution of x2 of t is equal to integration of 0 to t x1 of t minus tau x2 of tau d tau I wrote. So this is represents these two signal convolution cases. From the definition of Laplace transform, we take for the Laplace transform of x1 of t convolution of x2 of t is equal to integration of 0 to infinity. Then this one I take for the x value. I should substitute here. That is integration of 0 to t x1 of t minus of tau x2 of tau d of tau e power minus st d of t. I make to write as per the statement of Laplace transform. Then I take it out for the integration of 0 to infinity is outside. Then remaining portion I should write for the case of integration of 0 to infinity x1 of t minus tau x2 of tau d of tau e power minus st dt I make to write. Now I take for the t minus tau is equal to u. Then t is equal to u plus of tau and dt is equal to du. Okay. So this all value we can substitute for these equations. Then Laplace transform of x1 of t conversion of x2 of t is equal to integration of 0 to infinity integration of 0 to infinity x1 of u, that is this term is u, then x2 of tau d tau e power, here is t is a instead of t I substitute here u plus of tau d of u. Then rearrange the integration. So this case this equal to integration of 0 to infinity x1 of u e power minus u du integration of 0 to infinity x2 of tau e power st, that is s tau d tau. So this term as a Laplace transform I write as a x1 of s. This term I represent as a x2 of s. Now I prove if the Laplace transform in the case of time convolution in the input side, that is equal to the product of the respective Laplace transform input signal. This is called for the time convolution and multiplication property of Laplace transform. Finally I wrote the statement is x1 of t convolution of x2 of t Laplace transform is equal to x1 of s into x2 of s. Okay. Then Parseval theorem of Laplace transform. The Parseval theorem or Parseval relation of Laplace transform state that x1 of t Laplace transform is represented as x1 of s and x2 of t Laplace transform is represented as x2 of s, where x1 and x2 are complex function. Then I write for the Parseval statement integration of minus input plus into x1 of t into x2 star of t dt Laplace transform is equal to 1 by 2 pi j integration of sigma minus j infinity to sigma plus j infinity x1 of s x2 star of minus s star d of s. So this is called for the Parseval theorem or Parseval relation. Now we need to prove for this statement. So we take for the two signal, one is represented as x1 of t, another one is represented as x2 of t in the time domain. If we take for the both the signal in the Laplace transform, it's produced for the x1 of s and x2 of s. Based on this condition, I make to write for the inverse Laplace transform of x1 of t, that is represented as inverse Laplace transform of x1 of s is equal to x1 of t. Now x1 of t is equal to 1 by 2 pi j integration of sigma minus j infinitive sigma plus j infinitive, then x1 of s e power plus st d of s. Okay, this is inverse Laplace. That signal I should, that equation I make to write for here for the inverse Laplace transform. Okay, now taking left side of the Parseval theorem statement. Okay, so this Parseval theorem statement is a left side. I taking for the left side only. left side value is equal to integration of minus plus into x1 of t, x2 star of t, d of t. So now in this case, x1 of t, this x1 of t, I should substitute these values. Okay, in the inverse Laplace transform of x1 of s. So integration of minus into plus into 1 by 2 pi j integration of sigma minus j into sigma plus j into x1 of s e power st dt x star of t dt I make to write. Now, by rearranging order of integration in right side of what we are going to getting the equation, I take it out for the 1 by 2 pi j integration of sigma minus j infinitive sigma plus j into x1 of s, remaining term integration of minus into plus into x star of 2 t e power st dt d of s. Now this star I make to do for the whole star. Then if you take whole star in the sense here s also be going to take star, this plus I make to convert it as a minus minus. Okay, so now the equation I make to write as a integration of minus into x1 of t conversion of x2 of t dt is equal to 1 by 2 pi j integration of sigma minus j infinitive to sigma plus j into x1 of s integration of minus into x2 of t e power minus of star of t dt whole star d of s. So now this term, it will be look like a x2 of s. So I write for the x2 of s is equal to integration of minus into plus into x2 of t e power minus st dt. So what the term is present for the s, same like that we write. For here I make to write represent for the star. So I make to write for the star. This whole star it came here. So now the finally what the equation, our equation is going to consist of 1 by 2 pi j integration of sigma minus j infinitive sigma plus j infinitive x1 of s x2 of minus a star whole star of d of s. Okay, this equation I make to remodify as per the statement of Parseval relation. So the Parseval relation statement is represent by the output is going to represent by the 1 by 2 pi j integration of sigma minus j infinitive sigma plus j infinitive x1 of s x2 star of minus of s star d of s, same like that we received. Then our Parseval relation or Parseval identity is going to proved in the Laplace transform. Next case, we go for the solution of differential equation using Laplace transform. First, we take for the differential equation. So the differential equation is represented as an input as well as output side, both the case. That's why I take for the linear time system with the input is represented as x of t and output is represented as y of t, and the differential equation I make to described as some constant e of n d power n by dt power n y of t plus a n minus 1 d power n minus 1 divided by dt n minus of 1 dy of t plus up to a0 y of t is equal to b of m in the right side d power m divided by dt power m x of t plus b m minus 1 d power m minus 1 divided by dt m minus of 1 x of t plus up to plus of b0 x of 0. A of n and b of n, both the values are constant, that is represented as a real constant. So these differential cases for all initial values are 0. That means the differential initial values are 0 in the system of LTI cases. So now I write for the y of 0 minus equal to dy divided by dt 0 minus d square y by dt 0 minus equal to d power n minus 1 divided by dt power n minus 1 y of 0 minus all values are 0. That means input side as well as output side of initial values are 0. So input side, this is output side, input side x of 0 minus equal to d by dt x of 0 minus equal to d square by dt x of 0 minus equal to up to d power m minus 1 x of 0 minus 1 divided by d of t m minus 1, all values are 0. That means initial condition of the system we consider as a 0. Now we apply for the both the side as a Laplace transform in differential equation. The Laplace transform of a n d power n by dt power n u y of t plus Laplace transform of a n minus 1 t power n minus 1 m minus 1 divided by dt n minus 1 y of t plus Laplace transform of up to a0 y of n is equal to Laplace transform b of m d power m divided by dt power m x of t plus Laplace transform of b power m minus 1 d power m minus 1 divided by dt m minus 1 x of t up to l d0 x of t we make direct. So now if apply for this Laplace transform in all differential values, then initial condition we take in 0. That's why what I am writing a n s power n y of s plus a n minus 1 s power n y of s plus dot dot plus up to a0 y of s. Then x side also b of m x power m x of s plus b of m minus 1 s power m minus 1 x of s plus up dot dot up to b of x0. So both the side, the left side y of s is common term, we take it out. Right side x of s is common term, we take it out. Then I write for the equation is a n s power n plus a n minus 1 s power n minus 1 plus up to plus of a0 into y of s. And b of m s power m plus b of m minus 1 s power m minus 1 plus up to b0 x of s. Now we take for the ratio between the y of s divided by x of s. So this term it's go for here. Then x of s came for the left side of bottom. That is y of s divided by x of s equal to bm s power m bm minus 1 s power m minus 1 plus up to b0. Then divided by a n s power n plus a n minus 1 s power n minus 1 plus up to a of 0. So this term I represent as a zeros in the Laplace transform. This term I represent as a poles in the Laplace transform. Okay. So numerator all the terms it will be considered as a zeros and denominator we consider as a poles. So here we have the m zeros are present, n poles are present on this differential equation. So the Laplace transform, the equation is known as transfer function of LTI system in the Laplace transform. This value I call for the h of s. Okay. So the LTI system we are using for the Laplace transform, the y of s divided by x of s we call for the h of s. This h of s is represented as a transfer function. I make to write for this differential equation in diagram representation. Now we taken for the Laplace transform, that is Laplace transform. The system response is represented as a Laplace transform, that is called for LTI, linear time invariant system. We give for the input is x of t, its producer output is represented as a y of s. So the LTI system I consider as a in the Laplace transform is x of s. So now the y of s is equal to h of s convolution of x of s. Okay. So this h of s I represent as a y of s divided by x of s. So this function we call for the transfer function, the system response. Okay. The transfer function of LTI system is defined as the ratio of Laplace transform of output signal y of s to the Laplace transform of input signal with initial condition or 0. Okay. I make to write as h of s equal to y of s divided by x of s. The response of system in the s domain is y of s equal to h of s into x of s. We take for the inverse Laplace transform for this equation. We got for the y of t. Y of t is equal to inverse Laplace transform of h of s into x of s. The equation S is known as zero state response of the system. If impulse function is the input to the system, then I make to take for the x of t is equal to del of t for example. Now, the x of s, if you take for the Laplace transform of x of t, is represented as a del of t is equal to 1. This is we studied for the last session. Then y of t is equal to Laplace transform of x of s equal to 1. You substitute here x of s equal to 1, then we got for the h of t. This equation is known as impulse response of the system. Okay. You take some example. Find the transfer function of the system which is described by following differential equation. That is d square by dt square y of t plus 5 d by dt y of t plus 10 y of t equal to 3 d by dt x of t plus 8 x of t. Okay. Here we neglect for the initial condition. Initial condition is equal to 0. And taking the inverse Laplace transform on both the side, the equation is represented as a L d square by dt square y of t plus 5 d by dt y of t plus 10 y of t is equal to Laplace transform of 3 d by dt x of t plus 8 x of t. Now, we do for the Laplace transform. For this Laplace transform is equal to s square divided by y of s. The initial condition 0. This Laplace transform pi s y of s plus 10 y of s equal to this Laplace transform of 3 d by dt x of t is equal to 3s x of s plus 8 x of s. Now, this y of s terms are we take it out. Remaining s square plus 5s plus 10 y of s equal to here x of s, left side we take it out for the x of s, this is a common term, we take it out, 3s plus 8 x of s. Then finally I write h of s equal to y of s divided by x of s, and in 3s plus 8 divided by s square plus 5s plus 10. Okay. This is the Laplace transform system response. Okay. Then up to this much I am going to stop this section. Then remaining thing we will see for the next section. This topic I refer from the signals and system and B. Lathi AV Openum for signals and system in second edition. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.